Hello everyone. So today we will be discussing some important reagents in organic chemistry. So whenever we are facing any question in based on organic, so the question can be of reagent type or mechanism type or the concept type. So reagent is like, so every reagent has a particular function which it is going to do on the compound. So there are some 80 direct reagents which we can remember. So these are spread all over our functional group topics. So I have collected almost 80 reagents for this video. So with these, we can directly predict the product by seeing the reactant and the reagent. So here is the list of all the important reactions in each functional group. So in the hydrocarbons chapter, we have these. And for alkyl halides and aryl halides, we have these. Alcohol ether phenols, we have these. And then carbonyl, we have these. Carboxylic acid and derivatives, we have these. And amines, we have these. So these are the important reactions, a list. You can pause and just take a look at them. So for now, the topic is important reagents. So there are almost 80 reagents. So let's start. The first reagent here is PCl3, PBr3 or PI3. These are called halogenating reagents or halogenating agents. What they do is they are going to take alcohols and they are going to convert them into alkyl halides. So whenever we have PCl3, we'll get RCl, PBr3, RBr, PI3, RI. Simple. These are called halogenating reagents. SOCl2 is also a halogenating reagent, and this will convert alcohol into RCl, but also it will convert acid, carboxylic acid, to RCl. So this is a really strong halogenating agent. So we also have a note here, SOCl2 with pyridine. So in alkyl halides, you could see that whenever we are using RCl and ROH and SOCl2, we will get RX. Here, the product is retention product. Means now the configuration of this the reactant is R, then the product will also be R. If it is S, it will also be S, the optical isomerism here. Now, whenever we are using pyridine, we'll get an inversion product. Okay, the mechanism is there in alkyl halides. You can go revise it. Okay, so and next one we have HCl with anhydrous ZnCl2. Here it is concentrated HCl and ZnCl2. This is called Lucas reagent. So this helps in detection of uh, in differentiation of primary, secondary, and tertiary alcohols. So whenever we are going to use concentrated HCl with anhydrous ZnCl2 with primary alcohol or secondary alcohol or tertiary alcohol. So whenever we are using tertiary alcohol, a cloudy PPT, a cloudy precipitate is formed very fastly. If we are using secondary alcohol, if the unknown one is secondary alcohol and we add concentrated HCl and anhydrous ZnCl2, then a cloudy precipitate is formed in 1 to 5 minutes or 5 to 10 minutes. So if the unknown is 1 degree alcohol, then the reaction might take place from 10 minutes to never. Okay, it might take even several days. Okay, so that's how we can differentiate primary, secondary, and tertiary alcohols. This is called Lucas test, and this is Lucas reagent. Now, next one we have KNO2. KNO2 is a reagent which helps in forming nitrites. So whenever we are using Rx in presence of KNO2, then we will get R, O, and NO. Okay, as you can see here. So if we want NO2 or a nitroalkane, then we can use AgNO2. Whenever we are using AgNO2, Rx AgNO2 will give us RNO2. And then the sixth reagent here is a strong base. For example, we have NaOH, KOH, K2O, Na2O, K2Cr, sorry, K2CO3, These all are strong bases. What is the role of base? Base takes acidic hydrogen. Okay, whenever we are using strong base, then we will get the strong base takes acidic hydrogen. Okay, so whenever in the reactant which we are dealing with has an acidic hydrogen, then remove it. So and make a cation. Okay, that is what base is going to do. Right. Now, there is also an important note here. Generally, alkenes cannot be oxidized. Okay, they are really tough to oxidize, but there is an exception. Tertiary alkenes, in presence of KMnO4, KMnO4 is a very strong oxidizing agent. It can convert it into tertiary alcohol because so if the alkane is like this, okay, um, like this. If this is the alkane, okay, I've done some so the algae is like this. Check it out. And whenever we are using KMnO4, this is the hydrogen here, this is tertiary alkane. So because of steric hindrance, this hydrogen is forced to leave. So KMnO4 will immediately oxidize it and convert it into 3-degree alcohol. Okay. Now, the seventh reagent is inorganic fluorides. Inorganic fluorides help in formation of um, fluoroalkyl halides, alkyl fluorides, or whatever you want to call. So RX, X is already a halogen, so this helps in halogen exchange. So RX can be converted into RF using AgF, Hg2F, or SbF3. This is given in alkyl halides chapter. And next one is SO2Cl2. SO2Cl2 is a really strong halogenating agent, and it is used in converting alkanes to alkyl fluorides. As you can see here, our ninth reagent here is hot alkaline KMnO4. Hot is important. Alkaline KMnO4. So hot alkaline KMnO4, as we have discussed in alkenes chapter, it helps in oxidative cleavage. So what it does is, so whenever we are having a double bond, CC double bond, so generally whenever we are talking about hot alkaline KMnO4 or cleavage, so we are going to break this double bond and put, and depending on that, we can write products. The mechanism is there in the alkenes video, or you can just revise it. So whenever we have a double bond CH2, it will immediately oxidize into CO2. Now, if we have a CH2 along with an R, if this is a secondary carbon, so then an acid is formed. Carboxylic acid is formed. So whenever we have a tertiary alcohol, or so primary alcohol is there, it will convert it immediately into carboxylic acid. Secondary alcohol is there, it will immediately convert it into ketone whenever we are using hot alkaline KMnO4. But when we have a tertiary alcohol cannot oxidize. So what it does is it dehydrates and then oxidizes using the power of this thing, oxidative cleavage. Okay, now let's discuss about cold KMnO4 or just KMnO4. Okay, whenever KMnO4 is used, cold KMnO4 can be used in forming diodes. Okay, this can also be used as test for alkenes. So whenever we have an alkene and we use a KMnO4, potassium permanganate, so KMnO4 is generally purple in color. So it will convert alkenes into diodes. So you can see two hydroxy groups are attached. And again, MnO2 is a side product. So the solution will be in brown color. So we have discussed also a shortcut for this car. Means if I take a cis alkane and a anti-addition takes place, then racemic mixture is formed. Okay. So whenever we are having a KMnO4 type of questions, we can use this kind of shortcut. Okay. So here and syn addition takes place. Syn addition. Now, dehydrating agents. So here we have 4 dehydrating agents, which are very important. Dehydrating agents, they are nothing but they do exactly what they are meant to do. They remove the H2O. Okay. Now, whenever in our product, if we have H and OH, something like that, and then we are adding P2O5, P2O5 is a very strong dehydrating agent. We are going to just remove water. Okay, we'll just remove water and then we'll make it an alkene. Okay, so here we have various dehydrating agents, and dehydrating agents are also used for converting amides. This is amide, and then whenever I'm using dehydrating agent, you see, so that is how cyanides are also formed. Nitrile group is formed. So dehydrating agents can be used for these also. These are the four important dehydrating agents. So we have concentrated H2SO4 or H3PO4. We have PCl5, POCl3 or P2O5. Okay. Now next one, bromine water. Bromine water is a very important reagent because there are many questions using bromine water. So whenever we have, so here I took a phenol, I can also take aniline. Okay. Whenever I use bromine water, bromine plus H2O, then I get tribromo compound, tribromo substituted compound like this. Sorry, bromine. Tribromo substituted compound, as you can see here, aniline or phenol. So, but in order to avoid this, I want only one bromine to be substituted. Then I can use CS2, carbon disulfide. So then there are two products formed. One is at ortho position, one is at para position, bromine and OH. Okay, this will be a minor product while this will be a major product. Okay, this is bromine water or bromine CS2. So you can photographically remember that whenever we are using bromine water, then a tribromo compound is formed. Okay, now PCl5. PCl5 is also an important halogenating agent, but it will just convert acids into acid chlorides. So PCl5 does this, just remove OH and put Cl. Now, SnHCl or FeHCl, these are very important reagents which we will be seeing in amines chapter. So what it does is, it will substitute nitro group with NH2. So it will remove nitro group and form an amine. Okay, this can be done using SnHCl. A very repeated question this is. SnHCl or FeHCl, then just remove NO2 and put NH2. Okay, now we have elimination reactions. I'm not going in detail into this. We will just see the main um, structure of this. If you want to see elimination reactions, you can see alkenes videos or you can revise alkenes topic. So elimination reactions are of three types, and then beta elimination is of two types. Seidel product is formed and Hoffman product is formed, which we have discussed in alkenes topic. So whenever we are talking about elimination, elimination can form two products, Seidel product and Hoffman product. Seidel product is where the formed alkene is more substituted, so it has to be more stable. And Hoffman is a less stable one. So whenever we are using alcoholic KOH, the reagent topic we are discussing here, so alcoholic KOH, whenever we are using, then Seidel product is formed. A normal, more substituted product is formed. But whenever we are using tertiary butoxide, this is tertiary butoxide. So whenever we are using tertiary butoxide or a heavy agent, so what will happen? Hoffman product is formed. That is a less substituted product. This you can see beta elimination. So we will take beta hydrogen. We'll remove beta hydrogen, right? So whenever we are using tertiary butoxide or a bulky base, then Hoffman product is formed. Now, zinc metal. Zinc metal helps in if we have geminal halides, that is two bromines like this or two halides like this. Using zinc metal, I can convert them into alkenes. This is a simple reagent. Now, here we are entering into our next part of reagents. So we have classified these reagents because it will be easier for us to understand the reducing effects and oxidizing effects of particular reagents. We need to know if we are using this compound is formed when we are using this reagent, right? So like that, we have some specific oxidizing agents and some specific reducing agents, right? So let us start with some specific reducing agents. Now we have H2 palladium, H2 palladium and coke, H2PDC. Now, whenever we have alkene, we'll do hydrogenation and the hydrogens will be added by syn addition. Okay, there is a very simple hydrogenation reaction. Now, second one is called Lindlar's catalyst, which we have discussed in various topics. So, Lindlar's catalyst is calcium carbonate in quinoline. Right. Now, we take alkyne and we do Lindlar's catalyst, then we get a cis alkene. So, in order to get cis alkenes, we use Lindlar's catalyst. So, if I want transalkenes or anti-addition I want to take place that wants to take place, then we can use Birch reduction. Birch reduction is Na and NH3 liquid. So the question can be like this: they can give alkyne and convert it using NaNH3, and they will ask if anti is formed. Okay, the number of geometrical isomers possible, or this will be cis or trans. Then we can just solve the question simply. Right. Now, Rosenmund catalyst or Rosenmund reagent, it is PaSO4 and quinoline. There is always a confusion between Rosenmund and Lindlar's. Lindlar's is CaCO3 while Rosenmund is BaSO4. Rosenmund helps in converting acid chlorides into aldehydes. Okay, so acid chlorides to aldehydes. This is a mild reducing agent. Okay, and if an alkyne is formed, then cis alkyne is formed. Okay, alkene is formed. Okay, I'm sorry, my bad. Alkene. Now, SnCl2 or HCl, this is called Stephens reduction. Stephens reduction helps in getting aldehydes. So here we can understand that by using some reducing agents, we can like instead of converting directly into whatever you call directly from acid to alcohol, not directly reducing, we are reducing at a middle step. Okay, aldehydes. So we are having RCN, a cyanide group with SnCl2 and HCl. So cyanide group reacts with SnCl2 and HCl to form amide, and amide on hydrolysis will give aldehyde. Okay, so this is called Stephens reduction. Now we have two reductions from alkanes topic. So these two are very important. So from carbonyl group, we are converting into alkane. Okay, so first one is Wolff-Kishner reduction. The names are important: Wolff-Kishner and Clemenson. So Wolff-Kishner reduction involves hydrazine. N2H4 is called hydrazine in presence of KOH and heat. So here the mechanism is not important. Just remove the C double bond O group and replace it with a CH2 group. That is called Wolff-Kishner reduction. So in Clemenson reduction also the same thing takes place, but in Clemenson reduction we are using zinc amalgam ZnHe in presence of concentrated HCl. Okay, this is Clemenson reduction. So the next one is from alcohol ether phenol topic. So it is the MPV reduction. So the name is not important, but then also it is something like Mervyn. Okay, I forgot. Okay, Mervyn Pernoff something reduction is there. So MPV reduction, the name is not important, but what is happening here is important. So we have an aldehyde or ketone. So the reagent here is aluminium isopropoxide. Okay, aluminium isopropoxide in presence of isopropanol helps in formation of primary, secondary, or tertiary alcohols. Right. So isopropanol. So whenever you can see isopropanol or this is isopropanol, right? So isopropanol, and we are having a keto group or aldehyde group. Okay. What will happen? This is a reversible reaction. Okay. NPV. Now we get alcohol. It reduces into alcohol, and then I'll get this thing, acetone. Okay. So whenever we have a aldehyde or ketone and it reacts with isopropanol and in presence of aluminum isopropoxide, then I get alcohol. If it is aldehyde, then I get primary alcohol. If it is ketone, I'll get secondary alcohol. And then acetone is also formed as byproduct. And in reverse reaction, when I take primary alcohol and add it with acetone, then I will get a aldehyde. If I take secondary alcohol, then I'll get a ketone. This is also reversible. Now, there are 9 remaining reducing agents: LiLH4, Dival H, NaBH4 in ETOH, in NaETOH, NaBH4 in AlCl3 diglyne, B2H6THF, and H2 nickel. So, the important ones here are these. These 4 are important reducing agents, and their functions we have to remember all of them, whatever they are going to do. Okay, and these are the rest of the reducing agents. Reducing agents we will see in whole organic. So here we can see we have a table. So whenever we have an aldehyde group, sorry, okay, whenever we have an aldehyde group, it will convert it into primary alcohol. Okay, so all of these reagents will convert it into a primary alcohol. Whenever I have a keto group, they will convert it into secondary alcohol. All of them will convert into secondary alcohol. So just remember that all these 9 important reagents, whatever they are going to do, they will convert all aldehydes and ketones into primary and secondary alcohols. So here, the important parts come. If we have acid can be converted into primary alcohol, and primary alcohol only when there is a really strong reducing agent. So here we have really strong reducing agents, that is LiLH4 in ether and NaBH4 in ETOH is generally what they ask. Okay, this is important. Right, this is important. Okay, ETOH is whatever they are going to ask. Okay, and it does not. LiLH4 will convert it into primary alcohol, while NaBH4 cannot convert it into a primary alcohol. But if we use AlCl3 and diglyne, then it will convert it into primary alcohol. And then you can see the table and then their corresponding products. Okay, but LiLH4, very important, is a really strong reducing agent, but it cannot convert, it cannot reduce a C double bond C. Carbon-carbon bond cannot be reduced because electron density is very high in the double bond region. So whenever we are having a minus I group, then what will happen? The minus I group will take the electron, it will decrease the electron density on carbon-carbon. So then it can reduce. So this becomes a very important exception, that whenever we have a minus I group with a double bond, then LiLH4 will be able to reduce it. If we don't have a minus I group, then it cannot reduce it. Okay. Now, we completed reducing agents. In the next video, we will see oxidizing agents and rest of the reagents. Right. Thank you.